Hello, my name is Brian Crafton, and I'll be presenting our work titled CIM-SECDED, a 40 nanometer 64 kilobyte compute memory RRAM macro with ECC enabling reliable operation. My co-authors are Samuel Spitalnik, Jung-Hyu Kyun, Wei Wu, Carlos Tortanaga, Vivek Day, and Arijit Rachowdhury. And we are from the Georgia Institute of Technology, the Daegu Gyeongbuk Institute of Science and Technology, and Intel Labs. First, I will go through the motivation and background, which are essential to understanding our research contribution. Then I will discuss the macro design and data we have collected. Next, I will detail the CIM-SECDED algorithm and hardware implementation. And lastly, I will show our results. Compute memory is an exciting technique that can greatly increase memory bandwidth and perform multiplication and accumulation on the bit lines of a memory array. We can illustrate this by comparing a compute memory array and a typical memory array. First, we swap out our sense amplifiers for analog to digital converters. And now we can enable multiple word lines at the same time and add the results on the same bit line. This additional functionality makes compute memory an excellent kernel for matrix multiplication, which serves as the basis for deep learning applications. For this work, we use RRAM, which is a popular choice for compute memory. It is a non-volatile filamentary memory, which means memory is stored by creating and destroying a filament. RRAM has a high resistance state and a low resistance state, illustrated by the plot on the right. And like other memories, these states follow distributions that resemble a normal distribution. The device variation shown here poses a major challenge for compute memory. It's not that device variation is specific to compute memory or RRAM, but instead that variation of each cell is accumulated when we read multiple cells at the same time. So what exactly happens when we read multiple cells at the same time? Let's see a toy example where we read 8 cells at the same time. Variation is increased because we have multiple noisy cells, and dynamic range is reduced because we encode multiple cells in the same voltage range. And what's worse, compute memory currently doesn't have a viable ECC scheme, so that's where this work comes into play. In this work, we designed our macro around a 256 by 256 RRAM array. The macro can read up to 9 word lines at a time and uses 4-bit flash ADCs to read the multi-level outputs. The references for these ADCs are generated using on-chip 8-bit digital to analog converters. We also have several additional modules that enable several features. First, integrated in this macro is shift and add logic. The module takes the output from the ADCs, shifts values by their corresponding magnitude, and then adds them together to implement matrix multiplication. Second is an iterative write verify controller. This module fine-tunes the RRAM cells by successively programming each cell until it falls inside the desired distribution. This helps increase on-off ratio and reduce device variation. Lastly, we have ECC, which is the basis of this work. This takes the digital outputs from the ADCs and detects and corrects errors. We will provide a detailed explanation of this implementation after the next few slides. Here is a micrograph of the test chip and a picture of the PCB. The chip is fabricated in TSMC's 40 nanometer RRAM and CMOS process. It achieves up to 100 megahertz clock frequency. It uses standard digital VDD of 0.8 volts and analog VDD of 0.9 volts, and it consumes 11.05 milliwatts of power. To better understand the device variation and on-off ratio of RRAM, we collected measurements after programming the RRAM using various voltage configurations. On the right, we show the resistance distributions of the set operation for the low resistance state and reset operation for the high resistance state. We collect the data for 3 different write voltages and show the distributions as cumulative distribution functions. From this data, we can infer the mean and standard deviation of the resistance values, and we observe that by increasing write voltages, we can reduce the standard deviation as a percentage of the mean and thus improve compute memory accuracy. However, we should note that this does not come for free. Increasing the write voltage is known to decrease the endurance of RRAM. So after understanding how these variations behave for a single cell, we want to understand how they affect reading 8 cells at the same time. To do this, we first wrote all the cells with a random uniform distribution, and then read 8 cells at a time. The result of this is presented on the right as a confusion matrix for 2 different write voltages. The confusion matrix shows the percentage of time the actual ADC output, or the number of low resistance cells, was interpreted as the actual ADC code. Obviously, we want the expected to match the actual, so the percentages along the diagonal represent correct operation. All others represent errors due to device variation. And so from these results, we should conclude 2 things. Compute memory error rate increases with device variation, and more LRS cells leads to higher compute memory error rate. This is observed because we sense current and not resistance. So a lower resistance yields higher current and thus higher current variation. To enable ECC for compute memory, this work makes use of two key observations. First, we really only see plus or minus 1 errors occur during compute memory. So if we look at a confusion matrix, we can see that the errors occur only plus or minus 1 off of the diagonal. To get a better idea of what is meant by this, let's zoom in and look at just one ADC code. So when reading 8 word lines and 7 cells are in LRS, we get this histogram. What we find is that, some percentage of the time we get errors, which is where samples occur outside the reference voltages for 7. But these errors occur only for 6 and 8, and they barely make it into these regions. Therefore, we can assume that errors will occur only plus or minus 1 from their true results. And the second key observation is a relatively old idea called residue arithmetic, which basically means that parity schemes used by traditional ECC works after summing multiple rows together, assuming only plus or minus 1 errors occur. Next, we will see how these observations can be used to enable ECC for compute memory by walking through an example. We will break down these differences into the 3 main components of SECDED: encoding, detection and localization, and lastly, correction. The 4-bit data we will use is shown here. To illustrate compute memory, we will also read 4 consecutive rows, and the ADC results are shown below the array. Next, we will encode the parity bits for localization. This is the same as SECDED. And the last encoding step requires encoding 2 sign bits that serve as a checksum for computing the sign. This is important for compute memory because we need to know if the error was a plus or minus 1. This is not needed in typical SRAM or DRAM because if an error occurs, you just flip the bit. So, if an error is detected during compute memory, we can compare the compute memory result with this 2-bit checksum to see if the error was positive or negative. So this concludes encoding, and the next step is detection and localization. As an example, let us assume that a single error occurs at the 3rd data bit. So instead of 3, we read 2. To detect and localize this error, we can use the same exact logic as regular SECDED. All we have to do is look at the least significant bit, or mod the ADC outputs with 2, as shown here. This is because of residue arithmetic, as we discussed earlier. And from here, we can perform localization the same exact way as SECDED, by translating this syndrome shown in the bottom of the panel as the bit address. Now that we have detected and localized the error, the only thing left to do is correct the error. This requires us to compute the sign of the error. To do this, we will compare the checksum encoded in our sign bits with the sum of the ADC outputs modded by 4. If we do this math out, we will get 0 for the ADC outputs and 1 for the checksum. And so 0 minus 1 implies a negative 1 error. We would then go add 1 to the 3rd ADC output to complete correction. So this is just one example and a brief overview. My hope is not to fully explain the technique, but to give an idea of how this technique works and what is required. Now that we have gone through the algorithm, we will see the implementation. First, we start with a matrix or a neural network. Next, the ECC encoding is done off-chip at the compiler level because RRAM is not written during inference. However, during inference, detection, localization, and correction are performed on-chip using a digital logic implementation. On the right-hand side, I am showing an architectural diagram for this digital logic implementation. The XOR tree and double error detection logic are the exact same as a SECDED implementation. The sign adder tree and sign lookup table are new additions to SECDED to correct for both plus and minus 1 errors. Next, we'll see the power and area cost for this implementation and some results demonstrating its effectiveness at mitigating errors. In terms of overhead, CIM-SECDED requires 1 additional parity bit compared to SECDED. So for 32 data bits, SECDED requires 7 parity bits, and CIM-SECDED requires 8 parity bits. To understand the area and power cost of CIM-SECDED, we show the percentage-wise breakdown of each component in the pie charts below. The 8 parity bits, read circuit, ADCs, and decoder logic cost 16.8% additional area over a design without any ECC. In terms of power, these cost 31.8% overhead over a design without any ECC. But for this power and area cost, we observe over 100x reduction in bit error rate on ResNet 18. I am showing bit error rate over the 8 layers we profiled in ResNet 18. The gray bars represent the results with no ECC, and the blue bars represent the results using CIM-SECDED. Next, we translate bit error rate to accuracy on ImageNet using simulation. we find that depending on the rate voltage used, CIM-SECDED saves between 3.9% and 16.3% accuracy degradation on ImageNet. In this work, we presented a compute memory RRAM macro with ECC. This ECC scheme is nearly the same as SECDED. The major difference is sign detection for plus or minus 1 errors. Our design reduces bit error rate by over 100x and only costs 16.8% additional area and 31.8% additional power, while achieving 43.1 TOPS per watt. That's all for my presentation, and thank you for listening.